curvature flow approach. About a mean curvature flow approach to the density of minimal cones. Go for it, Lou.
Okay. First, I'd like to thank the organizer for the invitation. So it's my pleasure to speak here. So my talk is going to lie at the intersection of minimal surfaces and the mean curvature flow. So I will start with explaining, set up the problem. So in this talk, I'm going to consider minimum cone. So C, it is minimal and also for simplicity, I will assume that the cone has an isolated singularity. So in this case, we call it a regular cone. So minimum means that the mean curvature of the cone equal to 0. So here, since we assume that the cone has an isolated regularity, so you can just think about this means that the mean curvature at everywhere on the cone except that the vertex is equal to 0. So this is mean curvature is just the sum of the principal curvature. So in other words, it's the average, the banding of this hypersurface in Rn+1. And from variational viewpoint, you can think about, so when you consider a family of perturbation of this cone, so then you look at the rate of change of the area. So you get the first derivative of the change of the area is actually equal to 0. So the critical points of the area functional. So regular means that, sorry. So the length of the cone which is usually denoted by L of C, which is just the intersection of C with the unit sphere. It is a codimension 1 smoothly embedded submanifolds of unit sphere. Okay. And without loss of generality, we will assume the vertex of the cone at the origin. So concerning this minimum cone, so there's an important quantity which we call the density. The density of this cone is defined as a theta of C, which is equal to the area of C inside unit size ball of dimension n+1 divided by omega n. So this omega n, it is just the volume of unit n ball. Okay. Okay. Right. So minimal cones are actually important object in the theory of in the regularity theory of minimal surfaces, because so the singularity of minimal surfaces so are modeled by this minimal cones. And also, so if you look at complete minimal surfaces in Euclidean space, when you take a look at the tangent cone at infinity or the blowdown limit of this minimal cones, minimal surfaces, then you see the minimal cone arise as the limit. So it's modeled asymptotic behavior of this minimal surface as well. So it's draw a lot of attention to study this property of minimum cone. So in particular, so in this talk, we will go interested in the lower bound on this density of this minimum cones. So what we know about that, right? So first, so this classical result of Allard regularity theorem, which can be think about as some epsilon regularity theorem for minimal surfaces. Okay, so which says that, so for each dimension n, so there exists epsilon that depends on n, such that if the cone is not flat, then the density of this cone is strictly bigger than 1 plus epsilon n. Okay. So this is called the epsilon regularity theorem for minimal surface, just because another way to apply this theorem is when you have a smooth minimal surfaces in R plus 1. So for instance, in like a unit size ball, and then if you know that the error ratio of this minimal surface is close to 1, then you can actually get a curvature estimate for this minimal surfaces. So so you can apply this version of Allard theorem to derive the curvature estimates, or vice versa. So they're basically equivalent, but this is since we're interested in this lower bound on the density of minimum cone, so we like to state this version here. So however, there's one issue about this regularity theorem, namely, so the proof is actually by argument, by contradiction. So we can only see that so there exists such positive epsilon n, but then we don't actually know any information about this constant epsilon in the regularity theorem. So the goal of this talk is to to try to gain some quantitative information on this epsilon. Okay. So ideally, we would like to find the optimal epsilon n, but then maybe that turns out to be actually a very difficult question, and only known like for very low dimension. So at the end of talk, you will see that even though we don't actually get optimal bound on epsilon n, but we can still get some explicit near optimal bound on epsilon n. Okay, so that's the goal to keep in mind for the talk. Okay, so then let's briefly review what we know so far for this epsilon n. Okay, so so this is basically equivalent to saying that so we're looking for the infimum of the density of this cone, which is non-flat minimum regular cone. Okay. By the way, when the cone is actually flat, so this means that the cone itself is actually hyperplane. So then you can see that the density is equal to 1. Okay, right. So to understand this question, so it's necessary to try to have an understanding of the space of this minimal regular cones. Okay, so a first observation is that so C is a minimum regular cone if and only if the link of C is a minimum surfaces in the unit sphere. Okay. So we want to make this reservation because in a minute you will see that we're going to appeal to the recent development in the theory of minimal surfaces in closed Riemannian manifolds. So, but let's first take a look at the situation in the very low dimension case. So, for instance, so if we take a n equal to 1, right? So basically, we are looking at the minimum regular cones in R2, right? So there's an so which means that so the curvature has to be actually 0 everywhere on the cone, because then the mean curvature coincide with the curvature in one-dimensional case, right? So in this case, so this cone is just bunch of union of rays. Right, so in this case, you can easily compute the density of the cone. So just because we know the geometry of the cone very well, right? So that's why, so for the majority of the talk, we're not interested in the extreme low dimension case, because we have a full understanding of the geometry of the cones. Okay, so now if we look at the n equal to 2, so now we look at the minimal cones in R3. So by this observation, it means that so we look for the minimum surface in S2, which means that it's the geodesic in S2, right? So this means that C has to be planes, right? Because the geodesic in S2 is just like a gray circle, right? So then that's basically generate the plane in R3, right? So so then we have also a good understanding about the space of minimal regular cones in R3. Then let's go to the next dimension, right? So for instance, equal to 3. So here we know that so Yale has a conjecture which says that so for there are infinitely many minimal surfaces in S3. Okay, and this conjecture has been proved in the generic case by Airy. Oh, sorry, he is actually considered in any 3 manifolds. Nevis, and also full generality by Johnson, right? So in particular, in in S3, right? So we know that there are infinitely many minimal surfaces in S3, right? So hence there are actually infinitely many minimal regular cones in R4. So here you may worry about, so you see the infinitely many minimal surfaces, is it possible they actually somehow generated by finding one minimal surface, then apply the isometry group of the ambient manifold to get infinitely many. So indeed, they can show that these are not not only infinitely many, but they actually geometrically different. So they're not actually isometric to each other. So they indeed genially infinitely many minimal surfaces. So in this case, so you get also infinitely many regular cones, regular minimal cones. So indeed, so this is true for n between 3 and 7. Okay. Right, so from n equal to 3, so we already see that so the strategy to actually compute the density of a minimal regular cone one by one fails, right? Because you have infinitely many minimal surfaces, and the way they construct actually is implicit. So you actually don't have a closed formula for this minimal surfaces in S3, hence no formula for the minimal regular cone in R4. So you can't actually to check the density of this minimal regular cone one by one. So you need some like a more clever way to do it. Okay, so nonetheless, so one can appeal to the proof of the Wilmer conjecture by Marcus Nevis. So a key ingredient in the proof of the Wilmer conjecture is to bound the area of minimal surfaces in S3 with genius bigger than equal to 1. So then you can translate their theorem to the density, the lower bound of density of a non-flat, of a minimum cone whose link has a genius bigger than equal to 1. So namely we get, so if we have a cone which is a minimal regular cone, and if the link cone has genius bigger than equal to 1, then the density of this cone is at least pi over 2. And moreover, the equality holds if and only if this link of the cone is a Clifford-Tauran. Okay. Right. Okay, so basically it says that if the cone has non-trivial topology, then you get a sharp lower bound on the density of the cone, which is equal to pi over 2. So on the other hand, so there's a classical result due to Almgren. who give a classification of minimal surfaces of genus 0. So if we translate his theorem to minimal regular cone, it says that, so if so minimal cone, and if the link of the cone has genus 0, then the cone is actually a hyperplane. Right here, maybe. So then you combine these results. So one see that if you have a non-flat minimum regular cone, then the density of the cone is at least pi over 2. Okay. Because you give me any non-flat minimum regular cone, so then I look at the topology of the link of the cone, right? So I have two situations to consider. Either the genus is 0 or not 0. But then by Armstrong's theorem, if it's 0, then I know that the cone has to be flat. So that's giving me a contradiction. Hence, the link of the cone must have a genus at least 1. So then I use the Marcus-Nevis result to see that the density of the cone has to be pi over 2. And then you can also appeal to the equality case where you get the rigidity theorem as a Cliffordian. Okay. So basically, so in this particular dimension, which is n equal to 3, so one see that, so to derive the the optimal lower bound on the density of this non-flat minimum cone, so it's divided to 2 steps. So the first step is to try to see that try to get a relationship between the topology of the cone or the topology of the link of the cone with the density lower bound of the minimum cone. And then the second step is to try to prove some unique geometric uniqueness when the link of the cone has a simple topology. So that's basically how the strategy work in n equal to 3. So naturally, one would like to see if we can actually generalize this result to higher dimension. So it turns out that it's not so easy. So first of all, we don't have a similar geometric uniqueness for minimal regular cone with trivial topology in higher dimension. And second, we also don't know how to generalize this Marcus-Nevis results here to higher dimension, because so their argument using this min-max theory, so there's certain like a construction strategy that you can carry out in higher dimension. But then there are also some, they also use some like a classification of this low index minimal surface in S3, which is absent in higher dimension. And also some like estimates about the genius in the min-max construction is also not clear in higher dimension. So it's unclear how you can actually generalize this strategy for n equal to 3 to higher dimension. So from now on, I want to switch gear. I want to discuss a flow approach to this problem. Even though at the first glance it's more natural to actually think from techniques from minimal surfaces, because we're talking about minimal cone, which can be think about as a singular minimal surfaces, right? So however, I'm going to show you that how you can actually think about the minimum cone as a special solution to a geometric flow, and then approach this question about the lower density bound for minimum cone from a flow perspective. Okay, so the flow we're going to use is the mean curvature flow. So I'm going to first define the mean curvature flow. So I'm going to consider a family of hypersurface inside the Euclidean space. And this is a mean curvature flow if it satisfies this equation. So it basically says that, so if I have some hypersurface sigma t inside this family of hypersurface, so then each point on this hypersurface is going to move by its mean curvature vector. Right, so each point is moved with velocity given by the mean curvature vector, then it's a form of family of hypersurfaces, and so it's called the mean curvature flow. Okay. Yeah. Okay, so this mean curvature flow, it is a, let me, sorry. It is a negative gradient flow for area. So this means that the minimal surfaces are steady solutions to this mean curvature flow. So here one can interpret this minimal surface by allowing some like a mild singularity. So I'm going to say that this include minimum cones. So now you see the minimum cones, they are critical points for area. And then you can also think about it as a steady solution to this gradient flow for area, which is mean curvature flow, right? But if we think about the minimum cones as a special solution to mean curvature flow, so besides this density of minimum cones, there's another quantity which is which turns out to be very useful in understanding the singularity formation of the flow, namely the entropy. Okay, so okay, so this is the coding Minkowski entropy. Okay, so let's take any hypersurface in this Euclidean space. So then this entropy is denoted by lambda of sigma. And maybe this is using the parentheses. Okay, so which is given by taking supremum of this Gaussian integral with varying center and scale. So here I'm integrate against variable x. Okay. Right. So the motivation to define this entropy is this is actually monotone under this mean curvature flow. Okay, so then this function lambda of sigma t is non-increasing in t. Okay. So in general, so you see by the definition of this entropy, right? So it's involve a calculation of infinite many integrals, right? So it's not easy to actually estimate the entropy. So however, so it's a consequence of a Huisking monoticity formula that, so if this sigma is actually some special hypersurface that I'm not going to discuss here, but I'm just going to tell you that the special surfaces include spheres. So for spheres, so there's a way to calculate this entropy by Andrew Stone. So he actually obtained this very beautiful sequence. Okay. And it's also easy to check that, so the entropy of hyperplane is equal to 1. And this entropy is always bigger than equal to 1. In other words, the hyperplane minimizes entropy among all the hypersurfaces. Okay, so what very much related to our purpose is the following observation. So namely, if C it is a minimum cone, then we have the density of the cone is equal to the entropy of the cone. Okay. So exactly because this observation that's actually connected, so the density and entropy, so an elliptic viewpoint and a parabolic viewpoint. So now if we wanna estimate the density of a minimum cone, so it's equivalent to estimate the entropy of the minimum cone. So, but if you think about the estimated entropy of the cone, it's more natural to explore the techniques in the study of a mean curvature flow. And indeed, this has been explored before by other mathematicians. So here I just mentioned a couple of them. So first, so it is a result actually not really published, but you can find it in Jonathan Zhu's thesis. So he actually showed that for any minimum regular cone, and if the link of the cone is not isotopic to the standard totally geodesic sphere in Sn, then the density, which is also equal to the entropy, right? So it's bigger than equal to the quotient of the entropy of n-2 sphere and the entropy of the n-1 sphere. In particular, this is strictly bigger than 1 because this computation of stone, which shows that the entropy of the sphere is monotone decreasing with the dimension of the sphere. Okay. However, so this is not a so great result because so you can observe the computation tells you that so the entropy of the sphere going to convert to a limit, which is the square root 2. So then this means that as n tend to infinity, then you get actually the density of the such minimal regular cone is converts to 1, right? On that, and you know that there's a gap, and in minute you see that so this gap actually has some kind of lower bound. Right, but nonetheless, so this is the attempt of using mean curvature flow to derive certain explicit lower bound on the density for minimum regular cone with non-trivial topology, right? So note that so when n equals 3, so this condition here is the same to saying that the link of the cone has a genius bigger than or equal to 1. Okay, so it's just because when we talk about topology of surfaces, so all the things reduce to the genus, right? So they're all equivalent to the genus 0 or not. So however, when we go higher dimension, so there are many different ways to generalize its notion of genus, right? And a major source of inspiration for our work is this result of Ullman and White. We'll just so they show that so instead of consider minimal cone, but they consider area minimizing cone. And so they also need to assume the cone has a non-trivial topology in certain sense. So they actually has a various way to define that. So here I'm just going to present one of them, which is maybe the cleanest way to say that. So namely, so they assume that at least one of the components one of the components of the complement is not contractible. Then they show that, okay, so the density of the cone is bigger than or equal to the entropy of the n-1 sphere. And this in particular is strictly bigger than square root 2. And they also justify the result is optimal because one can look at this generalized Simmons cone. And then you check that density indeed convert to square root 2 SP or Q convert to infinity. So in other words, if you look for some dimension, some optimal bound that's independent of dimension, So under this topological condition, then the square root 2 will be the optimal bound. So on the other hand, so one can also check. So for each, but on the other hand, so for each fixed dimension, so their bound actually may not be actually optimal. Okay, so one important remark about their result is, so they state the theorem for any dimension. However, so it's a well-known fact that so there's no non-flat arrow minimizing regular cone in dimension less than equal to 6. So in other words, so the theorem is actually 1Q is true in those low dimensions. Okay, so then they made some questions in the end of their work. So one of the questions is to ask whether you can actually replace the irony minimizing condition by minimality condition. So with Jacob, we were able to address that question in dimension up to 6. So we consider n between 3 and 6. So, and we consider minimum regular cone satisfy the condition T. Then we show that the density of this cone is bigger than or equal to the entropy of the sphere, and is bigger than square root 2. Okay. So one can think about the result is like a complement of their result, because their results is 1Q is true in those low dimensions, so it only holds for higher dimension. Yeah. So then let me briefly mention some idea of the proof. So in their theorem, so why they assume this error minimizing is because they want to use this famous hard salmon correlation of error minimizing hypersurfaces. So, and plus mean curvature flow with boundary. So the main issue is that this hard salmon formulation only exists in higher dimension. So there's they not actually exist in low dimension. So that make their argument break down in low dimension, and and also break down for minimal regular cone, because that only exists near the error minimizing regular cone. So for our approach, so we will also use mean curvature flow, but we rely on heavily the theory of a self-expander. Of mean curvature flow. So let me just briefly mention what this self-expander is. So again, so when take a sequence, take a hypersurface in R+1. So this is a self-expander. If the mean curvature of this self-expander is equal to half of the normal part of the position vector. So it's called a self-expander is because if one consider rescaling of sigma by square root t. So this forms a family of hypersurface, and this is the solution to mean curvature flow. But as you can see that, so this is a very special solution in the sense that the shape of the time slice is actually unchanged under the flow. It's only differed by scaling, right? So, so the later time slice will be a scale up copy of the early one. So you see the things actually expanding along the flow. So that's called a self-expander. Okay. And so there are critical points of this expander functional, usually denoted by E. As you see, though, there's like a exponentially growing weight in this functional. On the other hand, so one can show that there's no compact self-expander. So when we say critical points, we really mean that we only consider variation that fix the infinity of these self-expanders, namely it's compactly supported variation. So the connection between this expander and the minimum cone is the following. So the minimum cone, first of all, minimum cone can be think about as a special example of expander, because you see the mean curvature is 0, and because it's a cone, then the position vector also tangent to the cone, so hence the right hand side is also 0. So it's a special solution to this self-expander equation. And more importantly, so there's a result by Qiding, which is built on early work of Immanen. So he showed that, so let's take, maybe I draw a picture. So let's take some cone. And let's assume this cone is minimum, but not area minimizing. Okay. And assume it's regular cone. So without loss of generality, we can assume the link of the cone is actually connected, right? So then the cone is going to actually divide the whole space into 2 parts. And then Qiding applied this variational method to construct self-expanders on either side of this cone. Right, so this sigma plus, sigma minus self-expanders lying on either side of C, and they also both asymptotic to this cone C. Okay. So it's a little surprising because here we are talking about finding critical point to this weighted area functional, right? So usually if you do this for just a full area, right? So then you expect so when you go higher dimension, you will have a small singular set appears. So but here, so his result is actually true for any dimension. But you need to make sure that so the cone is actually not area minimizing, because if the cone is actually area minimizing, so then you may actually get a sigma plus sigma minus, they coincide, which is just the minimizing cone. Hence, you cannot actually get a smooth expanders. Okay, so here, if it's actually not error minimizing, then you can actually use this minimum cone as like a barrier. So then you actually can show that the sigma plus, sigma minus, they not coincide with the cone. And the reason he got actually this good regularity theorem without any singular sets is because he actually can prove that. So the mean curvature has a sign of sigma plus minus. So if the mean curvature has a sign, and this mean curvature is equal to half of the normal part of the position vector, this means that so sigma plus and minus, they are actually radial graph. Over a certain region bounded by the length of the cone, right? So then you can rule out the singularities in potential singularity in sigma plus, sigma minus using the graphicality. Okay. And for our purposes, it's very important because when you have this property here, so you can see that, for instance, if I look at sigma plus, so that if I look at the region of sigma plus that contain this vertex of the cone, that's going to be a star shift region. So in particular, it's going to be contractible. And moreover, the topology of the cone can be identified with the topology of the sigma plus, right? So likewise with the sigma minus, right? So then to understand, to compare the topology of the two components of the complement of the cone is reduced to understand the topology of sigma plus, sigma minus. Then you can appeal to our early work, which says that if the cone has a small entropy, then the sigma plus, sigma minus, they are isotopic to each other. So then you basically can use this result to actually compare the topology of the components of the complement of the cone through the comparison of the topology of sigma plus, sigma minus. So hence they all same. So hence they has to be all trivial. If a priori, you know that entropy of the cone is very small, right? But we know that the entropy of the cone by observation is equal to the density of the cone. So then this leads to a contradiction. Hence, you actually get the lower bound on the density of the cone. So that's how you conclude the theorem using the theory of self-expander. Okay, so I think to conclude the talk, so I would like maybe mention a couple open questions. So right, so first it will be, I would be very interesting to know if our theorem can be extended to higher dimension. Right, so suppose you can actually extend to higher dimensions, which means that you get some optimal bound on that's independent of dimension for the density of minimum cones that has non-trivial topology. So hence you can think about so it's a higher dimensional generalization of this Marcus-Nevis results in dimension 3, right? So then you basically conclude the first step in try to deriving this optimal bound for minimum non-flat optimal bound on density for non-flat minimal regular cones, right? Of course, then to conclude, you still need to consider the situation that when you have a trivial topology, how you can actually prove this geometric uniqueness. But at least that's finished half of the program, right? And another interesting direction to explore is the higher codimension, right? So all we talk about is actually also makes sense in hierarchical dimension. So you can define the density of minimum cone of entire codimension, and also you can also define mean curvature flow in hierarchical dimension. With codimini-causal entropy also extended to hierarchical dimension in an obvious way. So it will be really nice to see to which extent you can actually discuss the density lower bound for the minimum cone of general codimension. So this is a couple of questions I personally found very interesting to explore. And I think I ran out of time, so I should stop here. Thank you for your attention.
Thanks for the nice talk, Lou. Do we
Thank you
have
for
any?
having me.
Oh yeah, sure. Do we have any questions from the audience? I have a quick question. So do you expect that this optimal density has a dimension independent bound that's bigger than 1?
Mm-hmm. Yeah, I think so. Yeah, at least under the if we assume this topological condition T.
Sure. Yeah.
I would expect it should be square root 2.
And
Yeah.
without the topological condition, you think still there should
I
be a
still
gap?
feel it's maybe possible because I always think the Simon's cone should be the best minimum cone, right? So
Yeah.
if they actually approach square root 2, I would still believe. But on the other hand, they do satisfy this topological condition, right? So, yeah.
Okay. And are there any like reasonable lower bounds that exist in the higher codimension case?
Actually, now that I know, I would imagine maybe you impose maybe some symmetry, then you may first make some conjecture, and then you try to see if you can actually proving something more general without assuming the symmetry.
I see.
Another direction is like, for instance, maybe not just the general hierarchical dimension cone, maybe you consider some like Lagrangian cones, maybe.
Right.
That's maybe more hopeful.
Or graphical.
Yeah. But I'm honestly speaking, I found the hierarchical dimension is at least with my experience in mean curvature flow, it seems like much harder than the codimension 1 case.
Yeah.
So that's why I feel the first question, I think, is maybe more approachable. So there's some step. So it's mainly come from when we do this series of expanders, we always work with the smooth expanders. But I believe with the recent development, like in minimal surfaces, maybe there's some like a way to get around.
I see.
And to allow singular expanders with a small singular set.
I see. Other questions? I do have one more, sorry. So is there any other reasonable topological condition that you thought about? Yeah.
Yeah, actually, I only present one. In Tom Newman and Brown-Weiss paper, he has another theorem which relates so basically replace the topological condition T by saying that they have a non-trivial homotopy group.
Mhm.
Then you get better estimates on the density of the cone.
I see.
So our theorem has a version like because usually it's not easy to check whether it's a contractible or not. However, so it's more easy to compute the homology group. So then we have a version of theorem saying that if at least one of the components of the complement is not homologic ball, then you get the density of the cone bounded by n-2 sphere, entropy of the n-2 sphere. So it's slightly improved. We have that theorem just because there's a lot of way to actually check homology of things inside of homotopy group, right? So in general, it's very hard to compute homotopy group.
Right.
So by homology, you have many ways to compute. So just for maybe for convenience of application, maybe we thought it would be better to include that. But originally, we do actually wondering like whether we can have Newman and White's second theorem, which talk about a non-trivial M homotopy group to replace the energy minimizing condition by minimum. But our approach cannot do that. Yeah. So.
Okay. Thanks. Yeah, that's all my questions.
Thank you.
Anything else? If not, then let's thank Lou once more.